Okay. Thank you, Mr. Chairman. Welcome to our presentation to the experimental investigation on the net cross-section failure mechanism in the presence of cracks. This is the outline of my presentation. Let's go to the introduction. In this preliminary experimental investigation is set up to create insight on the fracture behavior of cracked plates with holes. The formula reported here quantifies the design ultimate resistance for tension members as the product between the ultimate tensile strength and the net cross-section area divided by the partial factor and further multiplied by a 0.9 factor. This 0.9 factor is justified by fracture mechanics considerations and considers the eventual presence of cracks. Its value is based on the assumption that either the fracture strength is larger than 0.9 times the ultimate strength, which is case A in this picture, or that the width of the crack stays within the permissible range, which is case B. This range is taken as roughly 10% of the width of the plate. As the first step of the experimental program, standard tensile tests are performed with an instrument testing machine with a capacity of 250 kilonewton to determine monotonic steel properties. The elongation is measured with an optic extensometer over length of 100 millimeter, and the tests are deformation controlled at a speed of 0.6 millimeters per minute. Then we also perform tensile tests on notched plate specimen using a hydraulic testing machine of 400 kilonewton. These tests have been made to create a reference with previous literature. The elongation is measured with an extensometer over the length of 100 millimeter and are deformation controlled with a speed of 1.2 millimeter per minute. The same machine we perform cyclic tests to induce cracks in some specimen. Thus, for the first specimen, we applied 5 strain gauges and a cot meter. 4 of the strain gauges are placed inside the hole, besides the hole, and 1 is placed inside. The clip gauge is placed between the clips in the hole. From the results, it is noticed that both methods were suitable for detecting the occurrence of cracks, but the cot meter resulted in a more sensitive measurement. For this reason, the cot meter was used for the rest of the specimen. After the crack had been detected, the tensile test was executed with the same setup as shown previously. Going to the test results, we find that the monotonic properties of the steel with a yield strength of 307 megapascal and ultimate strength of 430 megapascal. These values correspond with the properties of S275JR steel. After executing the tensile test on notched plate specimen, we observed a similar trend as in the literature. In this graph, the force is normalized over the capacity as calculated with Eurocode 3, and displacement is normalized over the displacement recorded at the peak load. The specimen has on average 15% more capacity than is calculated with Eurocode 3. Then we cracked specimen by cyclic loading and consecutively performed the tensile test. In this picture, you can see the fracture surface of a specimen that is cracked under peak loading, after which it has been subjected to a tensile test. In this specimen, a corner crack has occurred. Of the 8 tests for this part of the experiment program, 2 were tested too early, 2 failed in the cyclic loading, and 4 were successfully subjected to a monotonic tensile loading after cyclic loading. Then we cracked specimen. Something is not going right. These are the results of the pre-cracked notched plates. The graph is normalized in the same way as is done before. When we compare the results of the cracked notched plates with the uncracked plates, a reduction of tensile resistance and ductility is observed. However, the ultimate load is not significantly below the characteristic value of the design rule of Eurocode 3. We also reassessed the failed specimen using both option 1 and option 2 failure assessment diagram, considering the allowance for a constraint effect on the brittle side, on the brittle fracture side. We estimate the crack size from the fracture surface. The assessment has been done 3 times with 3 different loads at failure. First time considered the failure load, the ultimate load as a failure load. The second one was the peak load at which the load where the pop-in behavior starts, which was associated with stable crack extension. And the third assessment in which the load is identified by the intersection of the second line having 95% of the slope of the linear part of the graph with a load displacement curve. It seems that the load at the pop-in and the load identified by the second slope give the best agreement between the prediction of the failure assessment diagram and the experiments. In particular, for the brittle fracture ratio KR, we considered the corrected value for the fracture toughness higher than the plane strain fracture toughness calculated using the master curve approach, considering beneficial effects of the negative de-stresses. In any case, the location of the assessment points in the failure mechanism diagram confirmed that the dominant failure mechanism is ductile failure. For this reason, we think that the steel grade is for this steel is case A as reported in the commentary to Eurocode 3, since the fracture toughness is relatively high for low strength structural steels. Summarizing the test results, we see that the average of the tensile strength of the notched plate is 15% higher than compared to Eurocode 3. That also counts for specimens that are tested on cyclic loading, but tested too early. Cyclic loaded specimens have a slightly lower tensile strength with 97% of the calculated strength of Eurocode 3. Based on these results, we can conclude that the pre-cracked specimens exhibit a reduced strength and ductility as compared to the non-cracked specimen. Moreover, the ultimate resistance is lower than calculated with the design rule of Eurocode 3 when the partial factor is omitted. Taken into account the size of the induced crack, it can be stated that the design rule of Eurocode 3 effectively covers the potential effects of cracks in this geometry, and for the considered steel grade, the failure assessment diagram is able to predict occurrence of failure. I thank you all for the time. Are there any questions?